Welcome to class, students. In this class we are going to discuss a logic synthesis with Verilog HDL. Our discussion will continue on this. If arithmetic operators are used, each arithmetic operator is implemented in terms of arithmetic hardware blocks available to the logic synthesis tool. A 1-bit full adder is implemented below. Consider an assign statement here. Assign. You are using concatenation operator. The cout refers to carry out or sum of final MSB bit of sum. So cout and sum we are merging. So if in any case carry is generated, that is stored in sum. If you consider a 1-bit adder, A, B and C are of size 1 bit. Say suppose A value is 1, B value is 1. When you add these two, you will get a carry generated. Cin, suppose if you assume 0, and if you add, the final result will be 0. Sum will be stored, will get value 0, and cout will get value 1. So cout will act as MSB. So 1 plus 1 is, answer is 2, adder. So for 1-bit adder, when you use arithmetic operators A plus B plus C in, the result is 2-bit. If carry is generated, that will be stored in cout and some value is stored. So in this example, so 1 plus 1 with Cin 0, you will get 1 0, sum as 0 and cout as 1. Assuming that 1-bit adder, so here we are discussing what hardware is generated for this A plus B plus Cin. So you can assume your logic synthesis tool may assign or generate this particular hardware, where A XOR B, A XOR B XOR, if you observe, so sum is A XOR B XOR Cin. So you are able to get when A is 1, B is 1, Cin is 0, so you will get answer as sum as 0. Then here you will get AB, then A XOR B ANDed with Cin, A XOR B ANDed with Cin, and these two you are performing OR, A XOR B and Cin ORed with AB. This is your cout expression. If you solve further, you will get as AB, B Cin, Cin A, which is a carry expression or cout expression. These two are equivalent. Okay. Either it may select this hardware or to reduce the number or get the optimized solution. Logic synthesis tool need to convert your data flow description assign statement using arithmetic operators. It should convert to optimized gate level network. It may select this one. It entirely depends on which synthesis tool we are using. From synthesis tool to synthesis tool, the gate level netlist generated may be different. In this case, it is implemented like this: A XOR B XOR Cin for sum, A XOR B and Cin, or with AB for cout. If multiple bit adder is synthesized, the synthesis tool will perform optimization and the designer might get a result that looks different from the above figure. Now in the next example, this entire logic synthesis, what we are understanding is if a particular statement is written, how it is converted into a gate level network. Now in this example, if you consider a conditional operator, a multiplexer is inferred. Okay, we'll see this. Assign out, this is your output. I1 and I0 are inputs, and apart from that, one more select line S is also input. I0, I1 and S are inputs. Now it depends on value of S. If S value is 0, the output of NOT gate is 1, and S connected to second gate, this will be 0. Now when for one of the AND gate, if one of the input is 0, so the output of this second AND gate, it doesn't depend on I1, it will be 0. Now I0 value, say suppose it is 1, and here you are getting 1, that 1 value you will get at the output of AND gate. So this I0 is selected. When S is 0, I0 is selected. If I0 value is 1, OR gate output you will get it as 1. What if I0 value is 0? If I0 value is 0, in that case, for first AND gate, one of the input is 0, so output will be 0 of this AND gate, and second AND gate output is also 0, so OR gate, both the inputs are 0, so output you will get 0. So it implements I0, I1, select line, a 2:1 mux. So the gate level network, how the gates are used, 2 AND gates, 1 2 input OR gate and 1 NOT gate is used to implement this 2:1 multiplexer. In other way, we can write output in terms of expression also by observing the gate level network only. So it depends on S. If S is 0, S bar, then I0 is selected. If S is 1, I1 is selected, like this. A logic expression, we can write expression, Boolean expression. This is a block that we are developing, and your gate level representation, a gate level representation for conditional operator, it may infers a mux gate level representation. So we have seen here for conditional operator using assign, here we have implemented. For this, a multiplexer is inferred. This operation is converted to a 2:1 multiplexer equivalent gates. Now if you consider a if-else statement for analysis, if-else statement, a single if-else statements translate to multiplexers where the control signal is the signal or variable in the if clause. Say suppose if S is 1, out is assigned with I1. If S is 1, out is assigned with I1. If S is 0, out is assigned with I0. So here also we are getting the operation somewhat similar to the conditional statement that we have analyzed. For this if-else block, it will result the condition that we have written. S acts as a select line for the mux, I0 and I1 act as input, so it may infer a gate level description will be, it may infer a 2:1 multiplexer as we have analyzed earlier. So the operation, I can write it as the condition that we are written in if, that is S acts as a select line. If S is 0, I0 is selected. If S is 1, I1 is selected, and then that is assigned to output. This is the expression, Boolean expression, and this is a symbol 2:1 mux, and the gate level representation is shown here. So it is always better that when you write if statement, else part need to be written so that unnecessary hardware can be avoided. In general, multiple if else if statements do not synthesize to large multiplexers. The case statement, if you consider, the case statement also can be used to infer means it may generate a multiplexer. The above multiplexer would have been inferred from the following description that uses case statement. So the condition that we are given is it acts as a select line for mux. I0 and I1 are the inputs, output based on select line value. So it may infer mux multiplexer, this particular case statement example. So here you can write when S is 0, I0, when S is 1, I1, so this is assigned to out. So the entire operation, this S bar, I0, S, I1, okay, we can see here. This is S bar, I0, S bar and I0, S bar and I0, and this one S, I1, so S, I1, or will be S bar, I0, S, I1. So both in if, case and conditional statement we have used the example such a way that it infers multiplexer. It doesn't mean that always it infers multiplexers. For it depends on entire on the logic. Based on the logic that we write in if, case, okay, accordingly the hardware is generated. For large case statements may be used to infer a larger multiplexers. For loops. The for loops can be used to build cascaded combinational logic. For example, the following for loop builds an 8-bit full adder. For each iteration, for example, I equal to 0. So first A of 0 plus B of 0 B of 0 plus C is nothing but C of n. Cn. Then that will be assigned to C again, okay, C and sum of I. This is assigned to C and sum of 0. Next it will be A of next iteration A of 1, B of 1 and C, okay, C from previous stage. It will compute carry out here sum of 1, so on. This will continue. Finally A of 7, B of 7, C, and it will generate C sum of 7. So the for loop, whatever we have written, it is unfolded for each value of I in the loop, and that many here you can see an arithmetic operator. For each it may generate one full adder. So such 8 different full adders it may generate. It builds 8-bit ripple adder. Ripple adder means from this block carry generated, carry in A, B, A of 0, B of 0, sum of 0, and the carry propagated C for next block. Again next block A of 1, B of 1, sum 1, and then carry generated like this, so on. So it may generate a 8-bit ripple carry adder. What we have to observe is, when you use looping statements, for each iteration value the logic is unfolded and then hardware is decided by logic synthesis to generate gate level a network. The always statement can be used to infer sequential and combinational logic. For sequential logic, the always statement must be controlled by change in value of clock signal. Always add pause edge of clock, Q assigned with D. So here Q is output, D is input. At positive edge of the clock, it will assign Q with D value. This is inferred a positive edge triggered D flip flop. So it may generate these two particular statements may generate a positive edge triggered D flip flop, D as input, Q as output, and clock as a clocking signal. Similarly, if you consider this logic, always at clock or D. If clock is 1, Q is assigned with. So here also D is input, Q is output, a D flip flop is generated. When clock is 1, in that case Q is assigned with a D. Here D latch is generated because clock acts as enable here. For combinational logic, the always statement must be triggered by a signal other than the clock, reset or preset. For example, the following block will be interpreted as 1-bit full adder. Say suppose always add A changes, B changes, or C in changes. In that case, this particular always statement, C out sum, it may generate as we have discussed earlier, it may generate 1-bit full adder for some calculation A XOR B XOR C in. A XOR B XOR C in. This is your sum. And for carry, AB, then B C in A.